All right, so in this video today, we're going to go over 2-7 related rates final review. So we're going to go over the answers to what hopefully you've already tried. First question, it says, write H in terms of R and theta. Okay, so I have this picture here. I have this right angle. I have this triangle. The best way that I can relate an angle to some sides is to use a trig function. Specifically, I'm going to use the tangent function. I know that the tangent of theta is going to be equal to opposite, which is R, over opposite over adjacent, which is going to be R plus H. That's the whole adjacent. Okay, I want to solve for H. So what I'm going to do, I'm going to multiply by R plus H on both sides. So I'm going to get R plus H times the tangent of theta is equal to R. After that, I'm going to divide by tangent of theta on both sides. And so what I'm going to be left with is R plus H is equal to R all over the tangent of theta. To solve completely for H is equal to R over tangent of theta minus R. All right, so that's H in terms of R and theta. Next one, it says, find the rate at which H is changing with respect to theta when theta is equal to pi over 6. So think about this. Theta is perpetually changing in this problem. It says that the satellite has centers and it measures the angle of theta shown. So we're saying that theta is changing. The only thing that's constant in this problem is R. That right there is a constant, and I need to treat it as such. So what I'm going to do is I'm going to replace R with 3,960. So I know that H is equal to 3,960 all over tangent of theta minus 3,960. Now all I need to do is I want to know, hey, what's the rate at which H is changing? With respect. When I see this with respect, that is the denominator of my d something statement. So with respect to theta means that theta is in the denominator. I'm taking the derivative of H with respect to theta, so dh dt. So what I'm going to do is I'm going to take the derivative of this function with respect to theta. I'm going to take the derivative with respect to theta. So the derivative of H with respect to theta is going to be dh dt. I want to take this derivative, but I want to fix it first because it's kind of going to be not so fun to take the derivative if I do it the way it's written right now. So I'm going to say I'm going to take the derivative, I'm not going to take it yet. So this little symbol notation says I'm going to take it, but I didn't take it yet. Okay, I know that 1 over tangent, if I go back to my pre-calculus days, 1 over tangent theta is equal to cotangent theta. That is a reciprocal identity. So I'm going to replace it. dh dt is equal to whatever this derivative is of 3,960 times cotangent of theta minus 3,960. And we're going to say take the derivative of that. All right, this derivative is going to be a lot easier to take. So dh dt is going to be equal to, why am I saying dh dt? I'm so sorry. We should be saying dh d theta. Sorry, dh d theta. We're taking the derivative with respect to theta. So what I'm going to get is 3,960 times the derivative of cotangent of theta with respect to theta. That's going to be negative cosecant squared theta. I took the derivative of theta with respect to theta, so that cancels to 1. I don't need to write a d something statement, a Leibniz notation statement. Derivative of 3,960 with respect to theta is just 0. All right, well, all I need to do now is plug in pi over 6. So dh dt, oh my goodness, I'm so used to saying that. dh d theta is going to be equal to 3,960 negative times cosecant squared of pi over 6. And I'm going to go ahead and I'm going to get a value in my calculator. I'm going to go and put my mode into radian mode. I'm pretty sure because we're given thetas, I'm going to put it in radian mode. So negative 3,960 times, cosecant is the same thing as 1 over sine. So I'm going to say 1 divided by sine of pi divided by 6 squared. And then I'm going to go ahead and evaluate that. Okay, so what I end up getting is, I'm getting something weird here, so maybe not. Let's see. Oh, yep. I'm just gonna double check some stuff there. Okay, I'm gonna do multiplication. You know what? We'll just leave this unevaluated for now. I think my calculator, depending on the mode, we'll keep it as this for now. So my DHDT is whatever this is evaluated. And to go ahead and use units, I'm going to say that it's going to be, I don't think we are given any rates of change in this case. I don't think we're given any units of measure here. So we are going to just leave it as this. So this right here is what DHDT is. All right, let's move on to the next question. All right, so the next question says this. A point moves along a curve square root of x in such a way that the y component of the position of a point is increasing at a rate of 2 units per second. At what rate is the x component changing when x is equal to half? Okay, this is one of those questions you just got to draw a picture for. So I have this curve. It's the square root of x function, which looks like this. The question is, what I'm given is that the y component of the position is increasing at a rate. So if I'm talking about like how much am I going up, my dy dt is equal to 2 units per second. Question is, how far is it moving across? What's the dx dt? So really, what's dx dt? So if I think about it like this, I want to know, using the ordered pair, how fast is x changing and how fast is y changing with respect to time. So really all I need to do is take the derivative of this function. I have y is equal to the square root of x, and I want to take the derivative with respect to time, seconds. Derivative of y is dy dt. Derivative of square root of x is going to be 1/2 x to the negative 1/2 dx dt. Now let's just plug in what I know. Dy dt is equal to 2, 1 over 2, and technically this is going to be 1 over 2 times the square root of x, times dx dt. Okay, well I want to know what dx dt is. I don't know what it is, but I also know what x is. It gives it to me. So I'm going to replace x with a half. So what I'm going to get is that 4 times the square root of a half is equal to dx dt. And I got that just by multiplying 2 on both sides and then also multiplying by the square root of half on both sides. So whatever this ends up being, I'm not going to evaluate calculator stuff today. That is dx dt. All right, let's move on to the next. All right, so the area, all edges of a cube are expanding at a rate of 8 centimeters per second. So first thing, I'm going to draw a cube. Okay, maybe not my best work. Oh well. All right, so I have a cube, and it says the edges of the cube are all expanding at a rate of 8 centimeters per second. How is the surface area changing when the edge is 6.5 centimeters long? Well, the property of a cube, and I know I didn't draw this very great, is that all the sides are the same. So like this is S, this is S, this is S. These sides are all the same. So I know that the surface area of a cube is just going to equal the sum of each side added all together. So if I think about a cube, if I were to write its net for a minute, so if I think about the net of a cube, let's think about the net for a minute. Something like this. It's going to fold up, 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 up. Yep, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. There are 6 sides, and each of them have an area of s squared. So the surface area is going to be 6s squared. The question is, how is the surface area changing? Changing. When I see changing, I should think derivative. When the edges are 6.5 centimeters. So think about it for a minute. 6.5 centimeters is not a constant in this problem. The whole cube is changing the whole time. So I'm going to treat that as something I'm going to plug in later. So let's take the derivative. ds dt, so dsa dt, the change of surface area with respect to time is equal to The derivative of 6s squared is 12s ds dt. 12s ds dt. Well, it tells me that the edges of the cube are expanding at a rate of 8 centimeters per second. So the sides are expanding, the ds dt, the change in sides with respect to time is expanding at 8 centimeters per second. So I'm going to go ahead and plug in everything and solve for dS dt. So the change in surface area with respect to time is going to be 12 times s, which in this case s is 6.5, times 8, which is dS dt. We're going to solve that, and our units on this is going to be, it's a surface area. So think surface area is got to be squared. So our units are going to be centimeters squared per second. All right, let's move on to the next one. All right, an airplane is flying in an air with an airspeed of 275 miles per hour. The plane is climbing at an angle of 18 degrees. Okay, so let's draw a picture. So we have this plane here. It's climbing at an angle of 18 degrees. I want to know what's the rate at which it's gaining altitude. So if I think about it, how fast is the y changing with respect to time? How much am I going up with respect to time? It says the airplane is flying in the air at an airspeed of 275 miles per hour. And so what that is going to mean is, let me think about this. It's flying with an airspeed. I'm going to go with airspeed is going to be the hypotenuse, but I am not 100% sure on that. So I guess we'll say it's dx dt for now. And if you guys want to talk to me about that later, go for it. Okay, so we're going to say that this is changing at dx dt. So, and we're saying that that's happening at 275 miles per hour. The question is, if the plane is climbing at an angle of elevation of 18, what's the rate at which this thing is gaining altitude? So that's really all I want to find here. So in order to find this, what I'm going to do is I'm going to find a way to relate both pieces. Well, I know that tangent of theta is equal to opposite over adjacent. Tangent of theta is equal to opposite over adjacent. And so what I want to know is, hey, what's this value when theta is equal to 18 degrees? When theta is equal to 18 degrees. So theta equaling 18 degrees is not a constant in this problem. It's not really a constant, and so we're not going to treat it as such. And what I want to do is I want to find the rate at which this plane is gaining altitude. So what I really want to know is what is dy dt. That's really what I want to know here. And so what I'm going to do is, real quick, I'm just going to solve for y. So we can say that x tangent of theta is equal to y. All right, so since this plane is gaining at 18 degrees, we can say that it doesn't say that anything about the plane changing its angle at which it's climbing, so we're going to keep that like it's a constant. Sorry if I said anything different before. For some reason in my brain, I feel like I might have said something. We'll see in the video. But we're going to treat 18 as a constant. It didn't say that it's changing its altitude its angle at any moment, so we're going to treat that like it's a constant. So what I have here is x times the tangent of 18 degrees is equal to y. All right, so all I need to do is take the derivative. Tangent of 18 degrees is just a number. You could look it up in your calculator. Let me actually just turn my calculator on and turn it into degree mode. The tangent of 18 degrees is 0.3249. We're going to keep it as tangent of 18, but think of it just as a number. So to take the derivative of tangent of 18 degrees times x with respect to t is just going to be tangent of 18 dx dt. And just if you're still unclear with that, let me just write what the decimal approximation is. This is the same thing as 0.3249x. So its derivative is just whatever this is, which happens to be tangent. That's going to be equal to dy dt. Okay, well, all I'm going to do is plug in everything I know. I know that dx dt is 275, and I'm solving for dy dt. So what I'm going to do is multiply by 275. I'm going to get 89.5 0.353. And the units on this, since we're talking about gaining altitude, is going to be miles per hour. And that right there is the solution. So that right there is the solution. All right, let's go on to the next one. This will be our last one here. Oh, never mind. All right. All right, so those are all of the questions, the question types that I wanted you to practice. Obviously, there could be more question types on the quiz tomorrow. I would make sure you know how to do a question involving a cone. Make sure you know how to do a question involving a cone. I'll do this over here. A cone, like this. Make sure you know how to do a question involving a sphere. Make sure you know how to do a question involving a right triangle. And just to be safe, maybe know how to do a question involving trig. So if I give you an angle. Those are the basic question types. I might throw in like a prism, like a cube or something like that. But those are the basic question types. It pretty much comes down to triangle, sphere, cone, and some sort of prism. All right, if you guys have any questions, feel free to contact me or meet me during office hours. And good luck on your quiz.